for joining this quick presentation on explainable AI with Erdre. Today is going to be a fairly quick introduction to Erdre and its feature for explainable AI. So we'll be going quickly through introduction to explainable AI very briefly. We're not going to go into any deep theory or anything like that before introducing the method we use, which is SHAP or Shapley values. Then a quick refresher maybe on Erdre. It's been presented before, and I think there is an existing video in the project on Erdre more in depth, but we'll quickly go through the pipeline as well as an example demonstration, which is going to be on the command line interface. So a quick introduction. Yeah, this. Yeah, quick introduction to explainable AI. I assume all of you here are familiar with machine learning and machine learning models. Um, they are for most purposes black boxes, which means we don't necessarily understand what's going on inside, and we don't necessarily understand what the output means, and that's not beneficial for building any trust or rapport with the machine learning models. So when now machine learning models and AI in general is more and more used for decision making, then we kind of need to be able to understand and trust the decision that's made based on AI or based on machine learning model. In addition to this, of course, if you don't, um, in addition to this, machine learning doesn't necessarily look at a problem the way we do. And if we don't understand exactly how it comes to a conclusion, it can be the case that flaws goes hidden. Maybe there is, for instance, an image where it's been trained on images with a particular color gradient, which might not work on images of a different from a different area, for instance. There are similar things that can that means that the understanding and comprehending why a model comes to the conclusion it does can be very beneficial. So that's why this is a fairly broad field of study, which has been growing in popularity alongside, of course, the machine learning sphere, and that doesn't seem to stop anytime soon now with the advances seen in GPT-4, for instance. So one of the methods used for this is called Shapley values. If you've heard or used explainable AI, you likely used Shapley values yourself, because this is probably, if not the most popular method for explainable AI, and it originates in cooperative game theory, which is a very old field, and it's then used to fairly attribute a player's contribution to the end result of a game. And in this case, we can consider machine learning model sort of like that game, and it thus evaluates the marginal contribution of each input feature, which is basically how much that particular feature contributed to a particular outcome. So that's generally computed by carefully perturbing or manipulating the input features and seeing how these changes affect the outcome. And then you can do that over a large amount of iterations and get an understanding of exactly how these features affect the outcome, both for a specific prediction as well as for the model in general. This is then computed with respect to sort of a background distribution, which represents the baseline or the default value. So you can see how much it is affected relative to said the baseline. To do this, we use SHAP, which is a very popular library for explainable AI. It calculates Shapley values, as you would expect, and uses then an explainer sort of to calculate the result. I'm not going to go into any details on the explainer. It's a fairly complex topic, but it has some value for the practical part as well, since the model architecture we use has an impact on which explainer we can use as well. In this particular demonstration, and the default now for the pipeline is the kernel explainer, which is an agnostic explainer, which means it works on all different models. But of course, that comes at a cost, as it usually does, with it being very computationally expensive. So if you're trying to run some explainable AI on, say, the edge or on a more resource-constrained environment, you can perhaps look into more tree tree-based algorithms like decision trees, random forest, etc., which are vastly more efficient due to the algorithm exploiting a tree-based or exploiting the architecture of the tree. So as you can see here on the right, you have basically the logo of SHAP, which with a quick explanation of how it allows you to understand the model better, with the very basic example here of seeing how each of these 4 features contribute to a certain prediction. So for Erdre, a quick recap on this, if you're not familiar with the pipeline. It's called the Erroneous Data Repair Pipeline, but that name is no longer enough to encompass exactly what it intends to do, as it's grown in scope since the remote set. It's developed and maintained by, and further developed by Erik Husum, which has also been doing a lot of work on InterQ. It's intended, and it does simplify the process of creating and inferring or using machine learning models, and allows for more efficient experimentation. For instance, it catches stages between different runs. So if you have done one thing like pre-processing feature extraction, you don't have to do that for each time you try new parameters or experiment with new methods for the data set. So it's used for both training and inference, and has been deployed as a Docker container now in the project, which has been successful to my knowledge. And as I said, it's continuously improved with new functionality. One of these, which is of course the explainable AI, which we're going to come to in a moment. So the stages for the pipeline, just very quickly, is pre-processing, which it takes care of for the most part. It cleans, extract features from a predefined set. It scales the data, or scales the features, really splitting the data into training and test sets before training, and then evaluating, of course, on a unseen set. It then discards the poorly performing models based on a set threshold, and then explains the models that qualified based on previous stages. This is basically the architecture as well. It goes through what I just mentioned. It gets data and configuration, reprocesses it, which is the 4 main stages I mentioned, and then trains an ensemble of models in the case of this particular version of the pipeline. So we train, I think it's 6 models for the baseline. And then we send these models and run test data on it and get the predictions for each. Then we evaluate which of these predictions or which of these models are valid candidates for the explanations, and then we explain it using SHAP. Then we get a combined set of explanations, which can look something like this. Because understanding the explanations isn't necessarily that straightforward, since the raw output of the SHAP library is, well, understandably, Shapley values, and this can depend a bit. The format can depend a bit based on the architecture of or based on the explainer chosen, rather, which means that direct comparison cannot always be done if you use different explainers for different models. And what we're really interested in, at least in this particular case, is not necessarily the Shapley values themselves, but rather a measure of feature importance. So how important one feature is relative to the others for the purposes of one single prediction, or also for the predictions generally created by the model. In this case, we have, in this case, the pipeline creates or calculates a number lower than 1, or 1 is the complete contribution, and then it calculates a number for each particular variable lower than 1, and makes that sort of a percent, makes that to be sort of the percentage contribution. As you can see here, we have an example using a test set from the project. We have the different architectures at the bottom. We have decision tree, gradient boost, light gradient boosting machine, random forest, stochastic gradient descent, as well as XGBoost. And of course, it goes up to 1, which is the complete, which is the cap, the complete prediction. Then we have the different features on the right. In this case, it's just raw data, no feature extraction done. So it gives us a fairly basic set of sensor data of variables rather. So here we can see that for this particular case, we have one variable standing out in almost all of the cases, which is position C of the accelerometer. And we have another, the one marked by red, which is PLC-R. These are not necessarily very human understandable features, but or human understandable variables, but still we get the relative importance for each prediction, or for each model at least. So here we can see that there are three particular features that dominate the or three particular variables rather that are very important for the prediction of this particular model. And then of course we have other ones that have far less weight on the prediction, and we see also a different architecture with a bit of a different view on the case rather. And this is why this can be quite valuable, because we see that all of these different architectures present a very similar view of the dataset, and then we can gain some confidence that this is quite reliable. But then of course we can see that this one doesn't quite agree. And I mean, of course, we can compare this to the particular performance of the models, right? They may not be all equal. Maybe this one performs better than this one. Then we can sort of get an understanding of the dataset at hand and also the prediction. So a quick demonstration using the CLI is not too visual in this case, but first we'll go over the dataset for this. For this demonstration, I chose a open source dataset. You can see the link on the screen as well as the reference to the paper in the bottom left corner. It's a quite simple dataset containing data from a triaxial accelerometer, which contains data from 3 machines. We use one machine and one operation for this demonstration. As you can see in the right-hand corner, it's annotated with quality. So the process or the operations are categorized into both normal and anomalous data, which we can then use to create a virtual sensor that tries to predict whether or not data is anomalous based on incoming unseen process data. So getting started is more of a technical step. I'm leaving it in case any of you want to try. But if you do, I recommend clicking the links or visiting these sites, which contain some background or some more detailed guides if you want to get it started. So I have done all of this already, of course, but you initiate the DVC, which is the version control for machine learning models. We do not necessarily care to track this with Git, so we add this flag, and then we input the data in a subfolder, which we then annotate with the dataset. Then we come to the parameter file. I guess I can, which I'm going to quickly just introduce the basics of. So name of dataset is basically where we placed the data. So I can open up a file here. Here's the source or the main directory, and then we have the parameter files here, as well as the asset files. And we want to go into data raw, and as you can see here, I have some data files containing the data sets. In this case, this is one we're using for this particular test. So we have an equal amount of good and bad data sets. Then again, I'm not going to go into the details on all of these variables, but we target the variable here with a name. So in this case, it would be quality, because that's what it's called, I think. And then we can decide whether or not we want to engineer features. So that's the feature extraction step. In this case, we do. So we can change this to true. And in this case, it adds sum, gradient, mean, maximum, all of these all of these features, it extracts these from the dataset based on the window size. So for 10 rows in this case, it will extract these features and use that as well for generating the prediction. And then we can remove the raw data as well. So if you want to take a look at the particular file for this example, I think this is the one. Yes. This is the name of the dataset, the target variable, the variables you want to include, all of the accelerometer data, X, Y, and Z. In this case, we want to engineer with all the features, which is more time consuming, of course, but for an example, this is fine. And we want to remove the raw data as well. So this is something that's often quite fun to experiment with. And it's made quite easy with Erdre. You just modify the different, you can remove and include different variables, add and remove features, as well as raw data. And of course, increase or decrease the window size for feature extraction, which can help capture rolling features or more time dependent features as well. Then split, scale, and sequentialize. This is just a training split, so 0.6 and 60% is used for training, 40% used for 40% used for validation or testing rather. Sequentialize, this is the window size that we use for actually generating the virtual sensor. We have target size 1, which is in this case the quality we generate. So whether or not it's anomalous or not, a 0 or a 1. We have window size, which is basically how much data we use or how many rows of data we use to generate this prediction. In this case, it's 1. Again, this can be improved or increased rather based on the particular case. For instance, in some cases, we wanted to use a whole file to generate a single output variable, which was like 7,500 rows, I think. But then, of course, you need more data. So we needed 500 or so files for that particular case. But again, this is very case dependent, but it can be fun to experiment with. Then train, if ensemble is set to true, we are actually using the ensemble explainer feature, and in which case the learning method doesn't matter because it uses a set of predefined architectures to run the ensembles with. I think in this case it's the 6 methods I already shown on the slide. And this is not relevant particularly for this particular case. It's more hyperparameter tuning because of course you do lose some control over the different architectures when you use a pipeline like this, right? It's trading convenience for control or minute control, but it's slowly being added back right here, at least for deep neural networks. And then evaluate, which is basically the metric for which models we want to include. Which depends, of course, on the performance metric chosen. For regression, it would be R squared usually. For classification, which this is, it's can be accuracy or F1 score, similar to those things. And then finally, we come to the explain part, which is well relevant for the explanations, in which case you give some inputs based on the background samples and summary samples, which are used to generate the average SHAP score or average feature importance for the model and not just individual outcomes or individual predictions. So the more samples you have on summary samples, the more times it runs the explanations, and the better or more accurate result you get when you want to look at the entire model, of course. And background samples is for the background data used as basis for generating SHAP values. So that was quite lengthy. But in this case, you can see this is the same file basically, containing the same feature or the same parameter sets. I think maybe some minor details change different, but nothing that's too strange. So since it caches everything I've done before, I can just change the explain stage. It should be able to just run the explanation stage. Again, this is not necessary for the running it at home, or this is just because I'm using a stronger server to be able to actually run the explanations in time for a demonstration. Otherwise, it would take a bit more time, especially since I'm running Teams as well. So here we can see it is running the explanations. So we set, I think, four samples. So now we're running, as you can see, one sample here at a time for each particular architecture, and it generates the explanations, or rather the feature importances, as you can see here. Of course, it's not too easy to understand it based on the rolling text right now, but at least this is to show basically how it works. So we can take a look at the actual performance as well for this particular model. As I said, the model was already cached, so this is the model we are running it on. You can see here we have a decision tree, gradient boost, light gradient boosting machine, random forest, stochastic gradient descent, and XGBoost. And you can see quite decent performance on all of the tree-based algorithms, and also all of the boosting algorithms, with an accuracy and F1 score of about 0.98, which is quite good. And the stochastic gradient descent is performing quite a bit worse, but not horrible. But again, this is dependent on the particular case, though XGBoost is usually outperforming the others, as is quite common, I think, based on the algorithm here, with an F1 score of 0.99. Now this is finished explaining as well, and then we can check in this case. This would then output itself into the data, not the data folder, sorry, the plots folder, and here we could watch the feature importances plot, similar to how we did it with the let me see if I can right, didn't open. Similar to how we did it with this, basically. So this is the predictions for this output. So we can see here all of the different architectures as previously shown, the different features. So we have frequency, slope, cosine, variance, standard deviation, etc. for all of the X, Y, and Z algorithms. And here we can see that for all architectures, though to a lesser degree, the stochastic gradient descent, the peak frequency of the Z accelerometer, or Z direction at least, is by far the most important, and the rest have fairly equal weight according to SHAP. So yeah, I think I'm out of time, and that was basically what I had. So now, if anyone has any questions, I'm open for that as well. Yes, Sagar.
Thanks for the nice presentation, Simeon, and I apologize for being a couple of minutes late.
Yeah, no worries.
Actually, you probably didn't mention the Rashomon effect, but you could, if you didn't, maybe you could explain how that relates to this.
Yeah, the Rashomon effect is basically when different models produce the same prediction, but based on different predictions, or based on different explanations, rather. Let's see. this case, I guess we see an example of that, right, where we have 5 models with very similar predictions, yet one with a completely different understanding of the dataset, but it still arrives at least a decent enough outcome.
So the 5 models have different explanations. So when you,
Yeah,
yeah.
or
So
at
when you
least
have an
these.
answer, yeah, go
Yes,
ahead.
we see these 5 have very similar explanations, right? They value the same variables to a similar degree, right? You see some minor differences, of course, but for the most part, they're very similar in their explanations. But despite this one being completely different explanations, it weights, for instance, a completely new variable that's not valued at all by these other algorithms. It still arrives at a decent enough prediction. Though, as we saw with the Bosch case, stochastic gradient descent doesn't perform as well usually as these other algorithms. So it could be interesting to see exactly why that is. But that's of course that's quite a bit more in depth, research.
Yeah, thanks. So
Yeah,
this
Asan,
question.
Asan, is it? I'm not sure if I'm pronouncing it correctly.
Yes, yes.
Yeah.
Thank you for the great presentation. And I was wondering, you in the one of the slides you mentioned that you average the predictions
Mm.
and you average the explanations. Why is it that you average the explanations? Why not just average the prediction and make one explanation out of it?
I'm not sure exactly what you mean with. You
Uh,
mean
if,
the
yeah, this slide and the previous
yeah,
one. The previous one where you had
right. Yeah, I think
I think it was before this one as well. Right after this, you show the flow of how Erdre works, right? And yeah, this one here. So you
yeah.
make explanation from one prediction and you combine these explanations, right?
Not explicitly. I think as I showed on the on here, I think we get we don't explicitly combine the predictions. We just get one prediction for each architecture, and then um, uh, we can use that to get sort of a larger understanding. So I'm not sure if we actually combine them explicitly yet, but we get multiple predictions and multiple explanation, which can sort of be uh, combined to get sort of an understanding, but not done in software at least.
Well,
In Saga,
Yeah.
if it's a classification problem, then you take the most frequently predicted class out of that,
Yeah.
right? The majority voting rule. But the explanations have to be different because the underlying architecture is different.
Yes.
And as you can see, the feature importances are different across different architectures. So, which also means that you cannot trust any one of these, and hence you need to somehow see what is the most which explanation has the most consensus across the models.
Yeah. Thank you.
So that's why we combine explanations as well separately. Yeah,
Separately. Yeah. Thank you.
I think Jürgen has a question, Simon.
okay, yeah, Jürgen, I can see the hands then, I guess.
Yeah,
Yeah, Jürgen, did you have a question?
muted Jürgen.
Sorry. Thanks for a great presentation, Simon. And I was a couple of minutes late, but I was wondering if you have like 5, is that 5 algorithms that are fairly similar, and one is gets very different results?
Yeah, to a degree, at least. All of
Yeah.
these, I would say, stochastic gradient descent is the most different algorithm to all these. Of course, decision tree and random forest are quite similar, right?
Yeah.
Both tree-based algorithms. XGBoosts are also often not. I mean, gradient boost, light gradient boost machine, and XGBoost are all boosting algorithms, right? So it's also quite similar, and they're also more similar to the tree algorithms than stochastic gradient descent. So it's not
Yeah.
surprising that if there is one outlier, then it is the stochastic gradient descent one, right?
So that means there is no incentive for picking one of the other from the five that performed well, or would you? Are there other criteria you could use to kind of to figure out which one would be perfect for this particular problem?
You mean the model as it
Yeah,
based on how it
yeah,
performs?
yeah,
Yeah, I think I would pick. I mean, in this case, I think the XGBoost performed the best, and you can see that it's also corroborated sort of by all of these other algorithms. So I would say that this explanation is quite solid, and I think I would choose the best performing out of these out of the models that had similar explanations, I think.
okay.
But
So you,
I mean, yeah, if you want to make a decision based on multiple different algorithms, then of course there are also other methods, right? Like
yeah,
uncertainty estimations and stuff like that, which could
yeah,
be considered.
yeah,
So I wouldn't
yeah,
just use this maybe, but it depends on the case.
yeah, because at least 3 or 4 of these methods, there's kind of insignificant difference. They look like they are more or less giving the same level of on the results.
Yeah, yeah, they are,
Great.
and
Yeah, yeah. Fine. Thank you.
yeah,
Thanks.
thanks.
I think the
Uh,
general the idea was to show that models can be different slightly, and you have a plethora of different models. So we will in future we'll extend it to neural networks and all other types of models and see how they vary. But the
yeah,
idea of using ensemble explanations is to uh, highlight the Rashomon effect problem that Simeon previously mentioned in machine learning. So that was the main motivation behind doing this. So I see Per has a question, Simeon.
yeah,
For
yeah.
you.
Yes, I just wondered, have you been thinking of, or can this tool be used to identify and help you set up the data quality monitoring for high critical AI usage? If I understand correctly, several of the models have chosen the same features as the most important ones.
Mm.
Can you dig further and elaborate on what is the quality thresholds of these features for the model to perform better, or continue to perform at the performance you need?
Right. So you mean based on this data, you can sort of investigate more in depth the threshold, as you said. So basically understand why it values these very highly, or
Yeah, well, I'm aiming for the system of system thinking of AI architectures where components are dependent on each other and they need some kind of contracts to be fulfilled, or either the AI ecosystem will collapse.
okay. So if I understand correctly, you mean basically using this information or this pipeline to get some thresholds for the different variables that
Yeah.
when exceeded can be then automatically or very easily detected, you mean?
Yeah, so far I understand you have just pointed out which are the most important ones.
Yes, yes.
Yeah, but can you use this information and can you elaborate further down and what is the quality thresholds for each of the most important ones?
Yeah, I see. But that is not something we do yet, at least automatically.
Yeah.
But it's a very interesting. It's a very interesting use case because yeah, that's also an additional that might be easier to put on the edge, as you say, right? Because while this again, it depends on the case because this is quite a lightweight virtual sensor, right? So you could use it directly to detect erroneous or anomalous behavior, I guess. But yeah, the thresholds would also be very interesting. But that's not something we do automatically, and I'm not entirely sure how to go about such a feature, but it sounds to me like it's possible, at
Yeah.
least. But it would require further investigation. Yeah.
Yeah.
Saga, did you have a comment?
Just a comment. Also, I think it's a very good thought, Per, and idea. So what I think is that when you know which input variables are kind of responsible for a certain prediction under ideal sort of circumstances, you can use them as constraints uh, on uh, on future processing. Like if you've deployed the model and you're predicting, let's say, toolware or something, and if the explanations do not match what you had, the features that you or input features that you had originally identified, then it could be a problem with the model processing the wrong kind of data among all that is available. Let's say so it's making a decision based on what was not previously determined as a causal variable. So once you know under controlled circumstances that these features are important, you make them into constraints of data quality, or let's say data relationship quality to decisions, and then when you deploy it, you want to make sure that um, uh, the model doesn't associate importance to other features that have not previously been identified. I don't know if that makes sense.
Yeah, and also for us, if you have a model that is you have 5, 10 most important features. If one of them are more or less missing or is delivering totally bad data for the new training set, will you be able to train the model with sufficiently performance? Because those kind of issues will happen in real life.
Yeah, so that's linked to uncertainty estimation a bit. So if your model exhibits high uncertainty in its prediction with new data, then maybe the data that you have is outside the scope of the model, the model's current behavior. So you will need to acquire more data in the new domain.
Yeah.
To do that.
But anyway, thank you very much for a very nice piece to the puzzle of better explanation and quality in AI. This is good.
Yeah, thank you. Thank you for your questions as well.
Are there any other questions?
Yeah,
There's
Roberto.
one from Roberto.
Hello, Simeon. Thanks
Hello.
for the presentation. Was very useful. Have one question regarding how did you run the pipeline? As I understand, you use DBC as
Yes.
the baseline framework, and you incorporated an explainability stage into the pipeline. Is that right?
Yeah, or Erik incorporated the explainability
Okay,
stage.
sorry. Okay.
Yes. But yeah, that's basically correct. Let me see if I can. Do you mean how to run it? Because there is sort of a tutorial on the and the links I provided in the yeah, the links I provided in the slides. So yeah, do you mean like the technical aspect of the installation?
Yeah.
Yeah. Okay. Yeah, it's basically, as you can see here, it's quite simple as long as you have managed to clone and install it based on the previously, like, basically it's very quite simple. Make a virtual environment. You use install pip3 install based on the requirements file, right? If you have Linux. If you don't, you can use the Docker container as explained here as well, right? It's been deployed once at least successfully in the project already, so it should function. In which case you just use the directions or instructions used here. So that should at least run on Linux, Mac, and as well Windows, at least on the VSL subsystem. But if you just want to install it on a native Linux, you can follow the installations on the Erdre site, which is basically you initialize DVC with, and in this case it was no tracking, but you can also use tracking. And then you add the data as mentioned, and then you just run DVC repro, which is what was basically done in this case as well. Yeah. So the scheduled job just runs. Sorry. Basically just runs this DBC repro, and that's basically it. Was there anything more specific you wanted to know, or?
No. Yeah, I just wanted a rough idea, and you explained very well. Okay. Thank you, Simeon.
Yeah, no worries. Are there
any other questions? Okay, no. So thank you so much, Simeon, and thanks to everyone for their time, and thanks to Carl for getting this presentation started for us. Simeon, you did a great job. Well done.
Thanks. Yeah, great to see so many people here. It was nice to have some questions as well. So thank you all for coming. And
I see Ketil has a question as well.
Oh.
No, I do not.
Okay. But good to see you.
Yeah.
Okay. Thanks, everyone.
Yeah, thanks, everyone.